Today I'm going to share with you some experiences that we had over the years on analyzing antibiotics in the environment. And when sometimes the wrong way, which we perceive is not the obvious thing to do, can actually take us to the right direction. So basically my goal today is share with you some of these experiences and not really to provide like results from our studies, but hopefully you will take some lessons from some of our experiences. Okay, so first I'll introduce to you why pharmaceuticals end up in the environment, including antibiotics. So I think many years ago now, almost 10 years ago, more than 10 years ago, we have shown that human and veterinary drugs are actually introduced into the environment through discharges from wastewater treatment plants because they are not really eliminated completely during the process of conventional wastewater treatment. And also from the spreading of manure from animal wastes. And because of this, we have found that antibiotics in the environment are actually persistent in soil and surface water. The very first paper that is now one of the most cited papers in environmental science and technology was published in 2002 by a group of people from the US Geological Survey, where they have shown that in surface water there's actually trace levels of antibiotics, hormones, other pharmaceuticals, and personal care products. And during that time, a few years after that, our group actually started looking at the fate of some of these antibiotics in soil. One of our very first publications was way back in 2005 in the Journal of Ag and Food Chemistry, where we looked at the persistence of tetracycline antibiotics and their degradation products in soils that had been amended with manure. And because of the laborious method for using liquid chromatography mass spectrometry, which is the conventional way of analyzing antibiotics and other pharmaceuticals in the environment, we decided to first screen the soil samples, because we have hundreds of samples, using enzyme-linked immunosorbent assay with the aim to reduce the amount of samples to be analyzed by LCMS. We also have one of our earlier publications, we have also shown that in wastewater treatment plants, the solid retention times are important parameters that dictate the removal of antibiotics. And then we have shown again in earlier studies that because of the differences in the treatment plants, in the design and operations, the vulnerability of surface waters to antibiotic contaminations is also highly variable. So some of these old studies had led us to know that antibiotics in the environment can actually stimulate the emergence of antibiotic resistance. And after 10 years, actually, the Obama administration have made an executive order to promote studies that will combat antibiotic-resistant bacteria. And so this has become a very important issue now on how to remove antibiotics in the environment or reduce the introduction of antibiotics into the environment. And in fact, in one of the newer or more recent issues of Chemical and Engineering News, it was featured in the front that we have a lot of research going on to look for antibiotics that are going to be effective in killing pathogens, because today it said here that today we face pathogens that are essentially resistant to all major classes of antibiotics. So analyzing antibiotics in the environment is very important. One of the things I wanted to first emphasize here is that antibiotics occur in many different matrices, not just in surface water or in soil, but also in plants. And of course, if you introduce manure and use wastewater for irrigation and manure to fertilize fields, or sometimes biosolids, we have actually shown that some of these antibiotics are taken up by plants, which potentially could end up in the food that we eat and in animals and the products of animals. So the low levels of antibiotics are also kind of drivers of occurrence of antibiotic resistance in the environment. So therefore, it is very important to develop methods for many of these different matrices in order to monitor for antibiotics in specific systems. So I want to share with you that we actually have two major research activities that will look at various ways of controlling and mitigating the spread of antibiotics and antibiotic resistance in the environment. One of them is funded by the USDA, and it's on the evaluation of the different manure management practices to control the spread of antimicrobials from dairy farms. And it's complemented by another grant funded by the National Science Foundation. And this one is more on looking at the antibiotics coming from human waste, from wastewater treatment plants, and how this receiving environment and the designs of wastewater treatment plant can either control or proliferate the dissemination of resistance. Okay, so the first thing we have to decide is what antibiotics should we analyze for? There are, of course, many different types of antibiotics, and we cannot possibly analyze for all of this. Even with the advent of state-of-the-art liquid chromatography mass spectrometry, we still have to decide which of these antibiotics are the most important. Unfortunately, it's not very easy to find information on the drug usage in humans, but I mean, even in the animal industry, we have data on the sales of antibiotics in food-producing animals, but it doesn't really tell you what animals and how they're used, could be therapeutic or for growth promotion. But at least this gives us a baseline information on what should we focus on. So you can see here tetracyclines are the most widely used in animal industry, followed by ionophores, like monensin, for example. Although ionophores is not a clinically important antimicrobials because this is only used for animals. Penicillins, macrolides, sulfonamides are the ones that are also widely used. So we actually monitor for some compounds that belong to these classes of antibiotics. Okay, so as I mentioned earlier, veterinary drugs are introduced into the environment because manure is used to fertilize fields. They are a good source for nitrogen, phosphorus, and they also improve soil water infiltration and improve the quality of the soil. But if you look at this data here from the EPA, you can appreciate how much manure is produced in the animal industry. This is only an example for a dairy farm. Let's say for 200 cows per day, they would produce about 24,000 pounds of urine feces. So per year, it's 8.8 million pounds. That's just a lot of manure that are being spread in soil, and this manure contain residues of antibiotics. Okay, so we start with I start with sharing with you some of our experiences in analyzing tetracyclines, which turn out to be a very challenging compound to analyze. But we have to develop methods for tetracyclines because, as you remember from the table, these are the most widely used antibiotics, at least in the animal industry. So the three compounds of tetracyclines, the three antibiotics in the tetracycline family that are used in cattle and swine, and I think also in chickens, are the tetracyclines, oxytetracycline, and chlortetracycline. So they differ by a few functional group. Chlortetracycline has chlorine group, and let's see, oxytetracycline has a, trying to see where the difference is here. Here, there's a hydroxy in the oxytetracycline, where in tetracycline there is none. So they're highly related. As I mentioned earlier, our very first study was to look at the persistence of tetracyclines in the soil, and we tried to use ELISA to screen for tetracycline to reduce sample load, and we thought that was the right thing to do so that we could reduce the expensive analysis by LCMS. But what we found out is that by using ELISA, so for those of you who are not familiar with ELISA, it's a bioassay that relies on the antibody, and it's a class-specific antibody that you can buy commercially. And it turns out that using ELISA to screen soil sample was actually the wrong thing to do, because in the end, so this is our data from this paper. Over a year, we actually detected tetracyclines as very high amount. So this is when we applied in May 2002. And we were hoping to only analyze by LCMS samples that show positive response by ELISA. In the end, all the ELISA samples turned out to be all positive and at very high levels, as you can see here. It showed that tetracycline was persistent, but it also showed that when we did the LCMS, because we basically end up analyzing everything by LCMS, it turned out the LCMS for tetracycline, oxytetracycline, and chlortetracyclines were much lower than the ELISA. So during that our initial reaction was, screening by ELISA is the wrong approach. And we wondered why there was a big discrepancy between the LCMS results and the ELISA. The reason for the high amount of, or the high results or concentrations of tetracyclines by ELISA is because the antibodies used in the ELISA cross-reacts with the transformation products of the tetracyclines. For example, chlortetracycline in the environment, depending on the pH and the temperature, can transform to epichlortetracycline. So it's basically epimerization here, okay? Change switch in this chiral carbon here. And then you have also the isochlortetracycline and anhydrotetracycline, which is removal of water. So because of that, we were detecting some of the transformation products of tetracyclines. And of the chlortetracycline and tetracycline have the same epimerization, where you have the anhydro and the formation of the dehydrated product and the epimerization. And it's the same thing for oxytetracycline. So it turns out that if you are only targeting by LCMS these three compounds, you will miss a lot of the transformation products of each of these individual tetracyclines. So it was actually in the end, our initial feeling of saying ELISA was the wrong approach actually led us to the right direction, because we realized back then that it's actually important to include the epimers of the tetracyclines in the LCMS method. And so now most of the methods that you will see in the more recent literature would include all of this. So so this is one example where the wrong thing that we thought was the wrong thing to do actually led us to the right direction, because now we are including all these compounds in our LCMS method. I mentioned earlier that tetracycline is probably the most challenging antibiotic to analyze. It's very sticky, it's very hard to extract and of course all these ephemeres and transformation products that are important because some of them are actually biologically active, and some of them are even more toxic than the parent compound. So we spend a lot of time optimizing extraction and analysis of tetracycline in soil for this study. Now I want to talk a little bit about LCMS. I know that probably all of you who are attending are familiar and or are using LCMS because it's now the conventional way of analyzing antibiotics in the environment. You must also know that there are so many different types of LCMS. The more simple one that we started 10 years ago was using a single quadrupole, which we now realize is not very useful for analysis of trace antibiotics or trace pharmaceuticals in complex matrices because it's not very selective. We actually moved to ion trap, which is good for characterizing transformation products that you do not know, especially for unknowns. But I think the most used type of LCMS is the triple quadrupole, the time of flight, which is a high res mass spec, and now more and more people are using Orbitrap. It's a little more expensive, but it's high resolution, and it actually has the ability to do low-level detection that the triple quad can afford. So it's a highly desirable method for LCMS analysis, but of course it comes with a price. So for now, I will focus mostly on triple quadrupole analysis because it's still the most widely used in the analysis of these compounds. But before you analyze using LCMS, you actually have to do a lot of optimization for solid phase extraction cleanup. And in fact, this is probably a more challenging step. Cleanup step is more challenging, I think, than trying to optimize the LCMS method. So the other thing that we have to be aware of is if you're analyzing for solid samples like soil or manure, you also need to extract it first from the solid before you can even clean it up and inject in the LCMS. So one of the more commonly used extraction technique is the accelerated solvent extraction because it's fast and it is the modern way of doing extraction instead of doing the traditional Soxhlet extraction, which is very long and tedious. So many researchers use accelerated solvent extraction to extract analytes at elevated temperature and pressure. And the conventional thinking is that the higher temperature, the higher you will have as a recovery, because you can increase solubility of the compound and you can increase the recovery. So that's the right thing to do. But you can see here in our graphs here where we evaluated the extraction of oxytetracycline and chlortetracycline using increasing temperature from 20, 40, 60, 80 degrees. And we also use two different pHs for oxytetracycline and chlortetracycline to change its adsorption coefficient in soil. But you can see here it is not true that the higher temperature you will have a higher recovery. It is true for to a certain degree, like from 20 to 40 you see an increase. But as you increase the temperature, you actually decrease your recovery. In the end, what we have decided to use for this extraction is to use 60 degrees because of the 60 degrees and pH 8 because of the reproducibility of the extraction. As you can see here, at 40 degrees it's higher, but there's a high variability in this condition. So, and this is a recovery of 30%. You might think is low, but that's actually common in tetracyclines. If you look at the literature, many of the extraction techniques are between 30 to 50%. So the most important thing is that it is highly reproducible. So again, the conventional way of thinking that if you increase the temperature, you will have a better recovery is actually the wrong way. So increasing temperature is not the right thing to do. Because if you increase the temperature, you also extract a lot of the matrix. And by extracting the matrix, you will see a lot of interferences in the LCMS. And I will show it to you in the next few slides. Here is an example. This is actually a trace using UV. So you can see here HPLC UV, which is the old way to analyze samples, environmental samples before, does not work for trace levels of antibiotics because you will see only this big blob. But if you have a mass spec, which is more selective, you can actually see the peaks of oxytetracycline, the epitetracycline, and so on. But you will still see this trace background coming from the co-extracted matrix. Okay, so there's still a lot of signal interferences, and the signal to noise is still affected. This is using accelerated solvent extraction. So actually now we decided that using manually, using sonication at lower temperature is actually the right thing to do. It's the right direction. So from while we liked the accelerated solvent extraction because it's automated, and if we have a lot of samples, we can switch the button and move along, and it's all done. But we actually extract a lot of matrix that affect our signal to noise. So now when we're analyzing for manure, we actually go through this extraction, which is manual, using sonication at 30 degrees, and then we do SPE using a tandem of amino SPE and HLB cartridge. You can see in this picture. And this, even with this method, we still see co-extracted matrix. When you're dealing with manure in soil, there's just no way to get rid of this matrix 100%. So you always have this issue. So we have developed a method that is acceptable for analysis of antibiotics and hormones in our project that is funded by USDA, where we collect samples from an advanced digestion system and also from lagoons. You can see here a lot of the things we have to deal with also is finding the right spot for the sample collection. We have lagoons. We also sample those that are spread in the field, but some dairy farms would have solid liquid separation where they press the manure and use the solids for beddings back in the cow stalls for bedding. So we also have to sample that, and then the liquid are used to fertilize the field. So we also have to do the runoff. And when you collect samples from all these various environments, even though you're dealing with manure in soil, you still have to evaluate your method because the detection limits is different for all these different matrices. So that's something to think about. In this project, we are looking for sulfonamides and all these different analytes in the sulfonamide class. We have to use a surrogate standard. In this particular project, we are using a deuterated D4 sulfamethoxazole and a C13 labeled sulfametazine. Unfortunately for tetracyclines, there are no labeled standards available, so we are using for internal standard or surrogate, we are using the meclocycline, which is a tetracycline class that is not approved for animals. So we can use that as an internal standard. We also look for macrolides, and we are using a C13 erythromycin labeled compound for surrogates or internal standards. And then we are also analyzing for ionophores. Again, ionophores, there are no deuterated or C13 labeled standards, so we are using this nigericin, which is not used in animals, and this nonactin, which is a similar structure. The surrogate standard are spiked before extraction, and we use the recovery of this to correct for the recovery of the other compounds. The internal standard is used after the extraction, and this is to check for the performance of the LC to make sure that the instrument is properly working. And it's that so if you don't see the internal standard, it's not because of the extraction, it is because the instrument is not working. So that's important to differentiate between the surrogate standard and the internal standard. So with all these various classes of antibiotics, it's actually not possible to, at least for us, for this instrument, and maybe it's possible for more advanced LC, but we have an old Agilent and Thermo LCMS. It's I think it's like 5 years old, but I'm sure I think the Orbitrap has higher capacity. But for now, with most of the LC-MS instrument, to optimize your detection limit, it's actually not ideal to put all these compounds in one method. So we actually have 3 methods when we're doing this analysis. We have a method that analyzes for sulfonamides and tetracyclines together. And then we have a separate method for macrolides. And then we have a separate method for ionophores. And by doing that, we are able to get the sensitivity that we need to analyze for these samples. And these are some of the published methods that we're using for sulfonamides and tetracyclines, which is actually including also the estrogens, but I'm not talking about estrogens today, just focusing on antibiotics. The macrolides method is described in this paper, and the ionophores are described in this paper. Okay. Before I go on to the next slides, I'd like to just kind of go back to the very basic of how a triple quadruple MS works, just to bring everyone in the same page. So the triple quadruple has these 3 poles. That's why it's called triple quad. So you have the first quad is where you separate, or we isolate, the molecular ions that you're interested in. So this is where the HPLC outlet is coming from. So this is where you separate your compounds based on times by liquid chromatography. And then if you're looking at positive ionization, so typically electrospray ionization is the most common, you will see, because it's a soft ionization, you will see molecular ion plus proton, and that's all the different mixtures that's coming out. LCMS in the triple quadruple is highly selective because you can isolate the precursor ion you're interested in. For example, in this figure, I'm interested in the red M plus H, and I isolate it into the collision cell, the Q2, and that's where I fragment it with collision gas. And during this fragmentation, you select the fragment ion you're interested in, and that's what you detect. You select it in the Q3, or the third quad. So by doing this, you're selecting in 2 stages, in the Q1 and in the Q3. So there's 2 stages of selectivity here, and that's why you can have a high signal to noise ratio when you're doing MS, or also called multiple reaction monitoring or selected reaction monitoring, depending on the brand of the instrument. And just to kind of make it clear in terms of what happens to these molecules, I actually took an example from a textbook. I know this is not an antibiotic, this is a pesticide actually, benzolphotione, but it's a good example on how MRM works. So I'm using it for just for now. Sulfatione, and I also wanted to show you that the M plus H is not always the molecular ion. It could be a fragment of the molecular ion, depending on the stability of the molecule. So in this particular example, the sulfatione actually fragments at the source. So the 308 is the molecular ion, but at the source, at the Q1, it loses a methyl group. So what you will actually see as M plus H is the M minus 15 precursor ion, and it's a 293 instead of 308. Okay, so it goes to the collision cell and it fragments there, And then the fragment ion that you can monitor is 263. So this is your MRM transition. And the presence of this supports the presence of sulfodione, and it's a good identification point. Okay, I mentioned earlier that the triple quadrupole provides a low detection limit because of the high selectivity during the MRM transition. You get rid of a lot of the background signals. In fact, we compared, so one of our very first papers back in 2005, back then I was actually, our group was using an ion trap. And so I used the data from our old paper, our LOD, for these different analytes, and compare it with our triple quad that we switched in triple quad in 2010. So this is not even a newer method or a newer LC. I'm sure that the newer LCMS have better limits of detection now. But even with our old LCMS, we have significantly lower detection limit for many of these compounds. So like erythromycin from 75 down to 9, sulfamethoxazole from 83 down to 1, and trimethoprim from 91 down to 29 nanograms per liter. So, so MRM using LCMS or triple quad is a very good tool for analyzing low levels of antibiotics. The other thing about MSMS is that you avoid false positives. So here is an example of an actual data that we have. So this is an erythromycin chromatogram with a retention time of 24.6 using a standard. And here is a chromatogram of a wastewater extract. And if you were only using the retention time, let's say you're doing a selected ion monitoring where you're only analyzing for one ion, you might mistakenly say that this is a positive detection for erythromycin because it's exactly 24.6 minutes and it has the 716 m/z, which is what you would see in a selected ion monitoring if you're only monitoring for one ion. But if you're monitoring for two transitions using triple quadrupole, you know that the transition from 716 produces a fragment ion of 522 and 558 from the standard. And the fact that these two fragment ions are not present in the wastewater effluent tells you that this is a false positive detection, and so you should not detect erythromycin in the actual sample. So that's one other positive identification for using a MSMS or MRM transitions in triple quad. The other thing I wanted to emphasize is to always look at the area ratios of these quantifying and qualifying ions using transitions. So this is a tetracycline standard. We typically, it's ideal to monitor at least two transitions, two MRM transitions. So the 445 is the molecular precursor ion, and the quantifying ion, which is the higher signal, this one, is 410, and the other ion, fragment ion, is used for qualifying ion, which is to basically confirm the actual presence of the tetracyclines. And this ratio is relatively constant. It could change a little bit, but it's relatively constant within, plus or minus 5%. So this is very useful when you're analyzing tetracyclines or other compounds in a dirty matrix. So I'll give you two examples here where it's a true positive detection. So this is the standard of tetracycline, and the area ratio of this quantitative ion and qualitative ion is 46.5. In the manure matrix, you can see, as I mentioned, when I say relatively constant, it's not exactly 46.5, but it's within 5%. So it's 49.3, and it's the same retention time and the same, about the same ratio. So this is a true positive detection for tetracycline. In another compound, though, sulfadiazine, this was a false positive detection that if we did not look at the ratio of the qualifying and the quantifying, we could have accidentally analyzed this and called it positive detection. But see here, the ratio of the quantifying ion and the qualitative ion is way off. It's 133 compared to 55. And you might say, well, you could say that the retention time is different, so maybe you could have just called it as a negative because the retention time is different. It's not always true, because actually matrix changes retention time. So if a compound shifts a little bit, it doesn't mean that it is not the compound, the target compound you're looking for. Here's an example. Tylosin, this is a standard, and this is tylosin in manure. The area ratios of the qualifying and the quantifying ions are almost the same, but the retention times are very different. So in the clean standard, the retention time is 16.228. In a manure matrix, it shifts, and this is very common. The shift in retention time with dirty matrix is observed many times. Okay, so the fact that the retention time shift, you should not call it as a negative right away. Ionization suppression, unfortunately, lowers your detection. I'm sorry, affects your detection limit. So I should have called it results in high detection limit. So because here is the compound signal, in this example is aminocycline, in a mobile phase, and if you spike the same amount, this is actually 100 parts per billion in matrix, you will get more than 50% reduction in signal. So your detection limit is affected. And probably the first thing that would come in mind if I would ask someone to say, oh, so what should we do to improve our signal, to increase our signal, what should we do? I think the tendency is that people would think we should increase the amount of sample so that we could increase the signal. Well, it turns out that if you increase the amount, so here, this is the original signal. If we extract 50 milligram of manure and you increase it to 100 milligram, this green one, the signal actually reduced. And as you increase the sample further to 500, it reduces further, and so on. So 1 gram, so the thinking of we should increase the sample size so we could increase the signal is actually the opposite. You have a decrease in signal when you signal to noise when you increase the sample. So more is not always better, and decreasing the amount is the wrong. You might think it's the wrong thing to do is to decrease the amount. You actually increase the signal to noise. So it's another example of unconventional thinking. Lastly, I would like to talk about analytical methods are not one size fits all. We have over and over have to develop and optimize methods for every single type of matrix. So our method that works for estrogen, sulfonamides, and tetracyclines in runoff and soil doesn't work for milk, for example. We have to optimize it for milk, and when we're looking for these compounds. And the same method does not work for wastewater. We have to analyze wastewater and we have to optimize it too. So finally, if you're looking for manure, we actually have to optimize it for solid fraction of the manure and for the liquid fraction of the manure. So that's something to keep in mind, that you always have to optimize your method for every matrix. And this is what I would like to discuss last. The wrong way around ionization is actually the right way. And I will explain to you what we mean by this. So typically when you do LCMS, you have to choose between positive ionization or negative ionization in electrospray. And more commonly, we have signals, better signals in a positive electrospray. So in a positive electrospray ionization, you want to ionize your compounds so that it's positively charged. And the right thing to do to make it positively charged is to reduce the pH, to lower the pH, make it acidic, so that you form a positive ion. That's the common conventional thing of doing sulfonamides, which has 2 pKa's, and depending on the pH, it could be positive, neutral. Here's a better example. Depending on the pH, it could be positively charged, neutral, or negatively charged. So if you're doing a positive ionization mode, your tendency might say, let's make the mobile phase acidic so we could have a positive sign. It's the same thing for tetracyclines. Tetracycline actually has 3 pKa's, and depending on the pH, you can have a positive, a negative 1, or a positive or a negative 2. So again, the tendency is to make, and most of the methods you will see in LCMS would use an acidic mobile phase to make this positive. However, we found out that actually making the solvent basic gives you a higher signal-to-noise ratio, and that's what we call the wrong way round ionization. You still produce the positive charge, that's why it's called wrong way round, even at a pH greater than 10. Here are some direct injection examples. This is sulfamethicin, and this is at a pH 2.5. It's the right way in a positive mode, and this is the pH 10.4. It is the wrong way round ionization. While the signal here looks like you have a higher signal at the pH 2.5, you should look at the background. So this is direct infusion. The background signal at the pH 2.5 is actually higher. So in the end, the signal-to-noise ratio is actually better when you have a basic mobile phase, and it works the same way for tetracycline. Now, it doesn't always work that way, because for erythromycin, the right way around ionization is actually better. So here, there are no there's not a lot of background, unlike here. Okay, so the wrong way round ionization is better for sulfamethicin and tetracycline, but not for erythromycin, because actually the background signal is low. And this is, I know this is not an antibiotic, but many of us are also interested in pharmaceuticals. But I want to point out that this wrong way around ionization works for many other compounds, not just antibiotics. So here, this is actually at the pH 10. Okay, the signal of carbamazepine in a positive mode is much higher than when you have an acidic pH. So this is another example of wrong way around ionization. We elaborate we propose a mechanism of why this is the case, and we publish it in Rapid Communication in Mass Spec. We suspect that we hypothesize that the presence of ammonium actually enhances the formation of positive ion by transferring the proton through ammonia in the gaseous phase. Okay, so lastly, organic modifier is another thing that we normally use. Sometimes we have to choose between methanol, acetonitrile, or something else. But I want to point out that sometimes the use of methanol may reduce your signal if you're using the molecular ion. So this is styrosine, which is a molecular ion M+1 of 916. If you use methanol, there's actually a formation of adduct that reduces the signal for 916 because you produce a 948 ion, which is an adduct of methanol. And we evaluated where the formation of the adduct happens. Is it the methanol in the diluent when you dissolve the sample in the vial, or is it in the mobile phase? What happens to when the adduct formation occurs? So here, when you have the acetonitrile in the sample diluent, using acetonitrile in the mobile phase, there is much higher molecular ion and low adduct formation. But in the same thing, when you have methanol in the diluent, it's still highly favored is the molecular ion. However, once you switch the mobile phase to methanol, the formation of the adduct increases a lot, and now it's the base peak. So it's very important not to use methanol for when analyzing for tyrosine. And again, this is another example of the wrong way, because so it is believed that methanol in electrospray produces higher signal. A lot of people have observed that methanol in general will give you higher signal in electrospray. And that's why most people use methanol, and that's the right thing to do. But actually, in this case, it's the wrong thing to do because the decrease in signal resulting from adduct formation will lead you to a lower signal. So it's better to use acetonitrile. One last example is the ionophore. Many of the publications, so ionophore forms sodium adduct, potassium adduct, and ammonium adduct. And if you're analyzing for monensin, the right thing to analyze is the highest signal, which is sodium adduct. And this is what the literature shows you. However, if you just follow everything and use the sodium adduct, you will miss out on a good signal because we actually did some study that sometimes for the other ionophores like lactulacid and narisine, for lactulacid and nonactin, the potassium adduct and the ammonium adduct are actually better. So you shouldn't automatically use what is in the literature and just follow the sodium adduct for analyzing ionophores. You should look at what the signals are, which adduct is higher. Okay, so to conclude, since we're running out of time and I would like to be able to entertain some questions, there's just two big take-home message here. That analytical methods are not one size fits all, that you really need to optimize methods for every matrix. To optimize extraction, cleanup, and analysis, all three needs to be tweaked for every particular matrix. And most importantly, don't always do the obvious thing because it's not always the right approach. The three things I mentioned here is that it's obvious to do acidic mobile phase when you're looking at positive mode. It's not always the case. It's also obvious to increase the temperature when extracting, because we think higher temperature, higher extraction efficiency, higher recovery. It's not always the truth. And increasing the sample size, we think should increase our signal. It's not always true. In fact, doing the opposite is better, reducing your sample size. And then lastly, just following the general recipe of using methanol because it's generally gives you higher signal in electrospray is also not always true because sometimes you could actually form adducts and it reduces your signal. So do not simply use the conditions that make sense. Evaluate everything if you want to have the best signal to noise ratio and the best reproducibility for the method. So with that, I would like to thank all my funding agencies and the students that have worked on these various projects. But the agencies where I supported my project are NSF, EPA, USDA, and WRF.